Alrighty, folks. So, as you can probably guess from all the writing on the screen, this is take 2. And I didn't realize something had gone wrong because nothing let me know it had until I had done a lot of calculations on the board. So what I'm going to do this time is just walk you through what I have here, and sort of say it out loud for the microphone. I'll probably be paranoidly checking the recording to make sure it's going at any given moment. And we'll just walk through the 2 sample problems that I have here. Right, so this is about section 9.2. It's where we're comparing 2 different population means, right? So we're still comparing 2 different mu's. And in this case, last time we were dealing if sigma was known and we had independent samples. This time we still have independent samples, but we're figuring out what to do when we don't know sigma, right? So if we don't know the population standard deviations, we got to do something else, just like we had to do in section 8.3 when we only had 1 mean, right? So we're going to be estimating the difference between the 2 means, same as we were last section. Our point estimate is going to be the difference of the 2 sample means, same as it was last section. Our confidence interval is going to be our point estimate minus E and our point estimate plus E, which is the same it's been since section 8.1. And we're also going to need both sample sizes to be bigger than 30 or both populations to be normal, right? And that's the same as last time as well. So one of the tricky bits about this section is that we have 2 different scenarios that we need to be careful of. We need to, one of them is if we think for some reason we have evidence to believe that the population standard deviations, remember this is the population standard deviation of the first population and the population standard deviation of the second population. If we have some reason to believe, if we have evidence to assume, if we have a reason to make a guess, then we're going to do it what's called pooled. And when we're in that situation, we have this formula for E, right? Same one's in the book. We're using T sub alpha over 2 here, right? Same as we did in 8.3. The minute we don't know sigma, we have to start talking about T's instead of Z's, right? So that holds true with what we've had before. We've got a little bit more complicated formula here in the square root territory, but it still just involves plugging things into that formula, so it's not so bad, right? And every time when we talk about T, if we ever mention that we need a critical T value, we have to know what the degrees of freedom are, right? So for every problem when we're dealing with comparing 2 means, when we don't know sigmas, then we have to figure out what the degrees of freedom are, right? Now, the other situation that we might be in is we might not have a reason to think that the 2 standard deviations are the same, right? So this is not the same, by the way, as only having reason to believe that they're not equal, right? If we have no information whatsoever, if the problem says nothing about the population standard deviation, then we have no reason to think it's equal, and we're here in the second case with unpooled data. So this one, we have to have a specific reason to use this guy, and if we don't have that specific reason, then we're in unpooled. Even if we might not have a specific reason to believe the opposite thing, we need evidence to move to here. Unpooled is what our default should be. Which is kind of nice because it does have a little bit simpler formula, right? This should hopefully be very familiar. It looks a lot like what we did last time, except again, instead of Z's, we got T's. So we need to know our degrees of freedom. And instead of sigmas, we've got S's, right? So same as when we did 8.3, the formula looked a lot like the formula from 8.1, except Z's were replaced with T's and S's with sigmas. So if we're in an unpooled situation like we are here, then we're going to do the same thing. We're going to take stuff from 9.1, We're going to replace the Z's with T's and the sigmas with S's. Okay, we're still doing good. I approve. Okay, so the first problem we had to work here, right? We talked about how the first sentence is basically setting us up to know that this is going to be a two means situation, right? A two sample situation because we have two procedures. The second sentence just sort of gives us some background. So it tells us, it gives us two different labels for our two different samples or two different populations. And the third sentence gives us our claim, right? So anytime where there's something talking about a claim, that's probably a sentence that is going to set up the question we need to answer. It's not a sentence that explicitly helps us find the confidence interval, right? So it's like in previous sections, all those sentences that we put a pin in, this is one of those put a pin in sentence and come back to it later, right? Now, so that was this sentence here, the one with the brackets and the arrow. So now we start to get some sample data, right? Tests usually tell us that we're getting some sample data here. Here we're also told how many subjects. That's another indication that this is talking about a sample that has to do with the original, right? That's where we got this piece here. That if we're doing a test that's taking a sample, it's conducted on 30 subjects, so the size of that sample is 30, right? And so this sort of is highlighting one of the things that I mentioned we could do in previous sections, which is that the subscripts 1 and 2 are really just placeholders to make sure we don't get the two different samples confused, right? It's never a bad idea, and it's often a good idea to, at least in the gathering data stage of things, name your two different samples so that you know where they're coming from, right? You don't just know that they're different from the other one, you know why they're different or how they're different, right? And then over here, we said the test, so that means the sample, with the new method, so that's our second population, was on 42 subjects, so the size of the sample of the new was 42. Right? And then the rest of the data was just listed off. There's nothing special to find that. They just gave it to us. And I listed it off here for reason I'll get into in a second. I want to look at this last sentence first, though. Test the claim at a 1% level, right? So before we've talked about confidence levels and things like that. But one thing to consider is that confidence levels are always supposed to be high, right? They're 80%, 85, 95, 99, 90. They're numbers in that sort of range, right? They're close to 1 if we're talking about decimals. They're close to 100 when we're talking about percents. So if you're given a level that's small, like 1%, that is a secret way of telling you alpha, not C. Right? Because alpha values are always going to be values that are closer to 0. 1, 5, 0.025. Alpha values are always going to be close to 0. So if it tells you a small percent level, it's telling you alpha, right? So that's why we have alpha equals 0.01 here. And we get C because C is always 1 minus alpha, right? So part of the reason why I repeated all this data here and laid it out, even though it was directly laid out in the problem, is because there's a way to do these problems that I haven't talked about much yet because I can't show it off, right? Our calculators can find any of these confidence intervals that we've been trying to find, way back since the beginning of section 8.1. The book talks a little bit about how to find those confidence intervals. So hopefully you've gotten the idea from there, but I just wanted to highlight the only reason I'm not showing it here is because the calculator app on my phone or on my iPad tends to make my iPad crash. And also it doesn't have all of the commands that a regular calculator does. But any of these confidence intervals that we found, you can find using your TI-83 or 84, probably other graphing calculators as well. You'll just have to look out what the commands for that are. The command on a TI looks like 2 sample T interval for this type of confidence interval, right? Each one has a slightly different one. This one is saying that it's a 2 sample mean. This one is saying that we're using T sub alpha over 2. And this just says that we're looking at confidence intervals. And for that, you need N1, X bar 1, S1, N2, X bar 2, S2, and you need your confidence level. You need C. And you need the fact that it's going to be unpooled. So we haven't talked about that yet, and I meant to before I started all this. But when we look at this problem, these words don't say anything about the population standard deviation. It says absolutely nothing about it. So since we don't know anything about it, we don't have any reason to think that it's equal between the two subjects, between the two populations. So we're going to be unpooled, right? And when you use the calculator, you need to tell it whether it's pooled or unpooled. So we're not. We're just going to plug into the formula. So this degrees of freedom, you don't need to find if you are using a calculator, if you're doing this 2 sample T interval command. But you do need it for the formula. So what we did here, this is unpooled, and our rule for unpooled is we want to take the smaller of the 2 sample sizes and then subtract 1 from it, right? So whichever one is smaller, so in this case, that's 30, is smaller than 42, so we take 30 and we subtract 1 from it. Right. And then we start plugging into the formula. And that's what all this work is, right? We plug in 11.9 for S1, 13.3 for S2, 30 for N1, and 42 for N2. And alpha is 0.01, so alpha divided by 2 is 0.005. Right? And then once we got to there, we needed to figure out what this T value was. So we know our degrees of freedom are 29, and our subscript is 0.005. So if we look back up at our chart, that's why I circled 0.005 and went down, and why I circled 29 and went over, and got 2.756 out of it. Right? So I plugged that in here. I plugged that into a calculator and got roughly 8.237. Right, so one of the things I did for these problems was I went ahead and calculated out our point estimate. So x bar 1 minus x bar 2, and I figured out that was negative 11.9. Then we plug it into our confidence interval formula. Plug all those values that we know in. And this was the thing I got in my head, so hopefully it's pretty close to correct. And then we need to interpret it, right? So that's always the big deal here. And for these, remember for these comparing two means problems, and this will continue on to next time, what we really care about is, are both endpoints negative? Are they both positive? Or is one of them negative and one of them positive? Right? In this case, they were both negative. And what that means is that we are 99% certain, right, because that was our confidence level, we are 99% certain that our difference of means is going to be negative. Right? Now, if we subtract two numbers and get a negative number, that means that the second one was bigger. Right? So the fact that both of these numbers are negative tells us that the average of values for the second sample, for the sample we labeled 2, are bigger, right? And if we go back up to our problem, 2 here was associated with the new sample, right? The sample with the new procedure. So we are 99% certain that the new procedure gives higher values on average, right? And then we got to go back to that sentence that we put a pin into, right? It is claimed that the values obtained by the new method are greater on average, right? So that's exactly what we found, what we're 99% certain of. So another way to state this interpretation is that we are 99% certain that the claim is correct because it matches up with this sentence right here. Right? So that's what we have for that guy. And next we had a problem talking about hotel room prices. Right? So, as we read through, it's talking about a survey. So we're pretty sure it's a sample. Surveys usually have to do with samples. And the next sentence confirms it, right? It says that that data here was obtained from 2 samples, right? So we know that this value then must be the average for New Orleans. That's what the subscript NO means. And this value must be the average for Phoenix. That's what the PH means. This sentence says the 2 samples had 61 hotels each. So N of both of these is 61. And our sample standard deviations are these guys. So we listed that out. And then the next sentence says past studies have found that the population standard deviation in the 2 cities are relatively similar, right? So that's the kind of thing that gives us reason to believe that the population standard deviations are equal, right? Or at least close to being equal, close enough that we should probably use the more complicated formula, right? So this sentence right here, right, past behavior tells us that we need to deal with this as a pooled situation, right? And lastly, the last sentence is sort of the question we should be answering with our interpretation, but it also gives us our confidence level, right? And again, this is specified as confidence, and it's a big number, so that's going to be what our C is, and alpha is everything that's left over, right? So this, again, would be the stuff that you'd want to put into your calculator. If you're using your calculator, you'd use the exact same command as last time. You just tell it that you want it pooled instead of unpooled. We're going to be using the formula, so we need to know what our degrees of freedom are. And when we're pooled, the degrees of freedom means we need to add up both of these guys. Right? So we get, let me make this a little bit more clear. Be on the right layer here. And get 120 out of it. Oops. Okay. I'm being really paranoid about that. I do not want to do this twice. So I apologize for that continuing to flash up on the screen, but I don't have any other way to check it. So, since we're pooled, we have this slightly more complicated formula. But once we plug in, we can start simplifying some things. We do need to figure out what our t value is. So we're going to take our degrees of freedom of 120 and our subscript of 0.025 up here to our chart. We get degrees of freedom 120, and we take that over. We get subscript of 0.025, and we take that down. These two guys meet at 1.98. So that's where this 1.98 came in. There's a 60 on every term up top, and there's a 60 on every term in the bottom. So I canceled those out. That's how we got this simplified thing. And these fractions have the same denominator, so we can combine them to get this fraction. Right? And then I plug it into my calculator, and I get something that's roughly this. Right? Then, same as before, I found our point estimate by subtracting the two means. Before I plugged it into here, just because that made the algebra a little bit easier to do. We plug in for that formula. I do some addition in my head and hope that it's right. And again, we want to interpret it, and the 3 things that we cared about is Are they both negative? Are they both positive? Or is one of them negative and one of them positive? Right? So in this case, they're both positive. And if you subtract two numbers and get a positive number out of it, that means that the first one was bigger. Right? So that tells us that the average values for whichever one came first are going to be bigger. Right? The population average is going to be bigger. So that tells me that since that was the one associated with New Orleans, right? That's why I like labeling them with descriptors rather than numbers, just because I don't have to go back and look at what the problem said one was. Right? But hotel prices in New Orleans are higher on average, right? We're talking about mu, so it's going to be on average, and both of these guys are positive, so we know it's higher in the first one than they are in Phoenix. Right, and this was our confidence level again. And so the question was, can it be concluded that the average hotel room costs more than in Phoenix? So we're 95% certain that yes, right? So again, we can't be 100% positive about anything, but we can come to a conclusion that most likely hotel prices in New Orleans are higher on average than they are in Phoenix. Right? So we're going to be doing this one more time, talking about mu's, except we're going to talk about it when we have a dependent sample. That's going to be coming up next. Then we're going to do this same sort of thing for comparing two proportions, and then we're going to move on to hypothesis testing. But that comes later, and I will see y'all then.